In this video, I'm going to explain about the automation tools. There are numerous tools on the market today. The following section presents many of the tools that are worth mentioning in the context of network automation, like DNA Center, Cloud Event Driver Functions, Terraform, Ansible, Chef, Grafana, Kibana, Splunk, and Python. Some of these tools are not fixed tools but rather modular tools that can be tailored and adapted to achieve data-driven network automation goals. This video focuses on such modular tools. Choosing the right tool for the job is as important in automation as is in other areas. When it comes to choosing a tool, it is important to evaluate your need against what the tool was designed to do. In addition, it is important that the staff responsible for using and maintaining the tool be comfortable with the choice. Note, for each of the following tools, we highlighted in bold the connection to previous illustrated use cases. Let me to start with the DNA Center. DNA Center, or DNAC, is a Cisco developed platform for network management, monitoring, and automation. It allows you to provision and configure Cisco network devices. It has artificial intelligence (AI) and also machine learning (ML) to proactively monitor, troubleshoot, and optimize the network. DNA Center, or DNAC, is software installed in a proprietary appliance, so you cannot install it outside that hardware. If you are looking to automate a network environment with only Cisco device, this platform is a quick win. Unfortunately, it does not support all device platforms, not even within the Cisco's portfolio. In the context of automation, DNA Center, or DNAC, ingests network data like SNMP, syslog, NetFlow, streaming telemetry from devices, parses it, and enables you to quickly complete the following tasks. Let me to explain about them. Set up alerts based on defined threshold. Baseline network behaviors. Aggregate several network metrics to get a sense of a network health, and act on outliers, and finally verify compliance status and generate reports. Let me explain a little about the setup alerts based on defined threshold. You can set up alerts based on metric pulled from network devices, for example, CPU, interface, or memory utilization. Alerts can have distinct formats such as email or webhooks. The next is baseline network behaviors. Baselining involves finding common behaviors, such as that a specific switch uplink sees 10 gigabits of traffic on Monday and only 7 gigabits on Tuesday. Discovering a good baseline value can be challenging, but baselines are crucial to being able to identify erroneous behaviors. DNA Center, or DNAC, offers baselining based on ML or machine learning techniques. Let me to explain about the aggregate several network metrics to get a sense of network health. Based on a vast amount of captured information, DNA Center, or DNAC, displays a consolidated view of the status of a network to give a sense of network health. It can quickly provide insights into devices and clients without requiring an understanding of metrics or logs. The next task is the act on outliers. Outliers can exist for many reasons. An attacker might have taken control of one of your endpoints, or equipment might have broken. Being able to quickly apply preventive measures can make a difference. DNAC, or DNAC, allows you to automate what action are taken in a specific situation. And finally, verify compliance status and generate reports. DNAC enables you to view and export network compliance verification and report from an appliance as an out-of-the-box functionality. DNAC is not as modular as some other tools, and enhancing its out-of-the-box functionalities is not supported in most cases. The next automation tool is the Cloud Event Driver functions. If you have a cloud presence, networking is part of that. One way of automating in the cloud is to use serverless functions. Cloud functions are event-driven, which requires a very specific data-driven automation type. Each cloud vendor has its own implementations, which makes multi-vendor environment very challenging. Developed code is not portable between different clouds even if they follow the same guidelines. Event-driven means actions are derived from events or changes of state. Events can be message, actions, alarms, and so on. An event-driven architecture is typically an asynchronous architecture. AWS, Lambda, Google Cloud Functions, and Azure Functions are examples of this technology. Say that you want to scale out your architecture, virtual machines or containers, when the CPU utilization of the current instances is high. You can trigger an event when the CPU hits a defined threshold and the cloud function provisions and configures new resources to handle the load. Event-driven functions also shine at interacting with many different components. They are typically used to automate the integration between otherwise independent components. For example, when someone tries to connect to a virtual machine but provide invalid credential, this action generates an event. The event can then be sent to a cloud function that creates a security alert or a ticket on the network management platform. Cloud event-driven functions are not limited to interacting with cloud components, although they run on the cloud. They can trigger actions anywhere, including on-premises. Now let me to explain about the next tool, Terraform. Terraform is an open source infrastructure as code IAC, infrastructure as code tool, with focus on provisioning and management. Terraform uses a declarative model in which you define the intended desired state, and Terraform figures out the best way to achieve it. That is, Terraform gathers the current state, compares it to the desired state, and creates a finite set of steps to achieve it. Terraform works best in cloud environment, where representing the infrastructure as code is easier. Terraform uses the concept of provider, which is an abstraction layer for the interaction with the infrastructure. It supports multiple providers, including the following, and the list keeps expanding: Amazon Web Service, Microsoft Azure, Google Cloud Platform, IBM Cloud, VMware vSphere, Cisco System. Terraform is command line interface CLI based, so you just need to install it on a workstation to begin using it. You do not need a dedicated server, although it is common to use dedicated machines in production deployments. Another option is to use the HashiCorp's software as a service offering, which is often preferred by large enterprises. To use Terraform, you define your desired resources in a .tf file. You will see how to do this later in this video. For more complex workflows, your files become increasingly complex. You can use modules. A Terraform module is a collection of files that you can import to provide abstraction to otherwise complex or extensive logic. It's important to note that Terraform stores the state of your infrastructure and refreshes that state before performing any operation on it. That state is used to calculate the difference between what you currently have and what is defined in your desired .tf file. Using Terraform to create a virtual machine on Amazon Web Services entails the following steps, which are illustrated with example. Step 1. Create a .tf configuration file. This is the step 1, creating a configuration file. Look at here. Terraform required providers is AWS, and after that this is the source and provider AWS. Profile name is default. Region is, for example, US West 1. And here you can see the resources that we work on it. Resource, AWS instance, EC2 name, and then some other information about it. Actually, we are creating a .tf configuration file in the step 1. Don't worry about the detail here, only we try to understand the structure, overall structure of the Terraform function. This is the step 1. Create a .tf configuration file. Step 2, initialize Terraform. As you can see here, we have this command Terraform init, and actually we are initializing the Terraform, and finally you can see Terraform has been successfully initialized. Step 3, optionally verify changes that are to be applied. Here you can see that we have Terraform plan, and as you can see, AWS instance with this name will be created. Okay, this is the remark, and here you can see which resource we work on it, and also some other information related to this resource. And then the next page of the Terraform plan. Okay, here you can see some information only for better understanding. You don't need to think about the detail. And after that, this page. Okay, actually in step 3, we optionally verify changes that are to be applied. Now let me go to the next step, step 4. In step 4, we apply the change with the command Terraform apply, and here you can see that AWS instance, for example, EC2 name will be created, and also here we have more information. And then you will see this page, okay, and also one more page. And this is the last page of apply the change. Here you can see, finally, you will have a question. Do you want to perform these actions? All of the actions that you saw, we should enter a value, yes. And here you can see that AWS instance now start to creating, and some other information actually are functioning. And this is the applying the change with Terraform. Let me go to the step 5. Step 5 means optionally verify whether the apply changes are as expected. With the Terraform show command, here you can see verify whether the apply changes are expected or not, or available or not. Here you can see, for example, about some of the configuration that we did before with this tool. This is the next page, monitoring false and some other information. For example, primary network interface ID, primary DNS, primary IP, public DNS, public IP, and some other information. This is the next page again, source disk check, subnet ID, tenancy, volume tags, and some other information that here we have. And finally, this page, root block device. For example, delete on termination is true, device name is this name, encryption, and some other information. This is the step 5. Because of that, about the steps, now we know that first we should create a TF configuration file. After that, we should initialize Terraform. And then step 3, optionally verify changes that are to be applied. Step 4, apply the change. And finally, step 5, optionally verify whether the applied changes are as expected. Actually, this example shows that you can provision a virtual machine in 3 simple required steps: initialize, plan, and apply. It is just as easy to provision many virtual machines or different resource types by using Terraform. Another advantage of using Terraform for provisioning operations is that it is not proprietary to a cloud vendor. Therefore, you can use similar syntax to provision resources across different environments, which is not the case when you use the cloud vendor's provisioning tools. Cloud vendors' tools typically have their own syntax and are not portable between clouds. Furthermore, Terraform supports other solutions that are not specific to the cloud, such as Cisco ACI, Cisco Intersight, and Red Hat OpenShift. Alright, the next tool is the Ansible. Ansible is an open source configuration IAC management tool, although it can be used for a wide variety of actions such as management, application deployment, and orchestration. Ansible was deployed in Python and has its own syntax using the YAML or YAML format. Ansible is agentless, which means you can configure resources without having to install any software agent on them. It commonly accesses resources by using SSH, but other protocols can be configured, for example, netconf and telnet. Unlike Terraform, Ansible can use a declarative or a procedural language. In this video, we focus on the declarative language as it is the recommended approach. Ansible uses a push model also. Ansible can run from a workstation, but it is common to install it in a local server, from which it can more easily reach all the infrastructure it needs to manage. Actually, we assume that the Ansible is installed now, and I want to show you about the using Ansible to configure a new TACACS Plus key. Okay, here we can see this command, for example, cat inventory.yaml, and here we have this information: all children, iOS, host, switch 1, Ansible host 10.0.0.1, Ansible network OS is Cisco iOS, and about the variables: Ansible connection, Ansible.net common.network CLI, Ansible user, then username, and Ansible password is the Cisco 123. In this example, Ansible gathers device information and changes the TACACS Plus key to a new one. There is a single Cisco device in the inventory file, and you can see that the key change succeeds for the specific devices. You could use the facts gathered to determine whether to make the change or not. For example, you might want to execute the change only if a source interface is defined. Okay, Ansible is very extensible. It can also be used to provision resources, interact with systems, collect information, and even perform network migration. Here you can see that, for example, we have the playbook.yaml, Ansible playbook to change TACACS keys for iOS devices. Host equal iOS, connection local, gather facts no, and task is named gather all iOS facts and some other information. You know that here we are reviewing only. Actually, we don't want to talk about the detail of Ansible here. And then Ansible playbook.yaml -i.inventory.yaml or YML. Here you can see that it plays, and here we have play, task, and also some other useful information. Do not be worried if you don't yet fully understand this example. Actually, we will learn about them in future with more details. For example, in future videos, I will describe Ansible's installation and concepts, including playbooks, inventories, and roles, as well as how to achieve common networking tasks. Ansible, you know, that is very extensible. It can also be used to provision resources, interact with systems, collect information, and even perform network migration. The next tool is Chef. Chef is a configuration management tool written in Ruby. It allows you to define IAC, but unlike the tool described so far, uses a pool model. Chef uses a procedural language. Chef configurations are described in recipes. Okay, collections of the recipes are stored in cookbooks. Typically, a cookbook represents a single task. For example, configuring a web server. You can use a community cookbook instead of building your own. Day cookbooks cover actually most of the common tasks. Chef's architecture consists of three components: nodes, Chef server, and workstation. About the nodes, a node represents a managed system. Nodes can be of multiple types and are the ultimate target you want to configure. Chef server. The chef server provides a centralized place to store cookbooks and their respective recipes, along with metadata for the registered nodes. Nodes and the chef server interact directly. And finally, workstation. A user uses a workstation to interact with chef. A workstation is also where you develop and test cookbooks. Chef is targeted at managing system as it requires the installation of an agent. Nonetheless, it can manage infrastructure that allows the installation of the agent, for example, Cisco Nexus 9000. Okay, the following examples assume that the Chef architecture is in place. Actually, here you can see Chef recipe to configure new web servers depending on operating system platforms. Okay, here we have package install web server do and then some other information. They are related to the Chef. Chef managed systems or nodes are constantly monitored to ensure that they are in the desired state. This helps avoid configuration drift.